Hello class, today I want to just briefly give you about a 5 to 6 minute lecture about allotropes. So the question I really want to ask today and then answer is, what is an allotrope? This is something that I've just been a little bit remiss about and have sort of skipped over. But I think it's important that you understand what an allotrope is. So I'll go ahead and give you the formal definition, which is allotropes are chemical elements that exist in two or more structural forms. The key here is elements that exist in two or more structural forms. So this isn't like if you have an allotrope of something like potassium or something. It's not as though they're different. They're different molecules or something. No, it's the same element. It's just sometimes they're arranged in different patterns and different geometries, and it leads to them looking differently. But they're the same elements. They're still, the same element K or the same element Br. And allotropes, the word itself comes from the Greek word that means other and grow, which kind of makes sense. So again, allotropes are chemical elements that exist in two or more structural forms. Okay? So moving on, I'm going to give you some examples of allotropes. And one of the first ones, probably the most important one, is carbon. Turns out carbon has three naturally occurring allotropes. It has diamond, graphite, and Buckminster fullerene. Graphite's the most common. Diamonds, of course, are much more rare. You notice that both of these allotropes have carbon arranged in a six-membered ring. It's just that with graphite you have these sheets on top of each other, which is one of the reasons why it leads to being a very good lubricant, and it is easily removed off of substances. And then you have diamond, where you have all this interlocking going on, and it's a much more tighter structure. Okay, and one of the things that I always found amazing was that diamond and graphite are both carbon. They're both the same element, but yet look at how different they are. They couldn't be more different in the properties they have and everything like that. In 1985, Buckminster fullerene was first synthesized. Despite this kind of weird cage, and it's a soccer ball shape, it actually is naturally occurring as well. And so it makes it one of the other naturally occurring allotropes. They do believe it floats around in space, but it's pretty difficult to make. But again, if you want to look back, there's a really interesting videos about the discovery and then the synthesis of fullerenes in 1985. Now, there are many more allotropes of carbon, basically because humans can synthesize them. And so on the right-hand side here, we actually have something known as a carbon nanotube. And this is, again, these are pretty high-tech in biomedical engineering right now. I have a little bit of experience with this in the sense that when I was in graduate school at the University of Michigan, one of the mentors of mine was a professor named Dr. Richard Lawton, and he was a person who made an allotrope of carbon way back in the early 70s called corannuline. And corannuline was actually kind of a half of a buckyball. So if you look at this little portion here, he actually made this bowl-like structure called corannuline of carbon. It was first synthesized in his lab at the time, was a big deal. In fact, the people who made Buckminster fullerene quite often pointed to his papers on that and proposed and thought that maybe there's a way to put two of these together and make a ball. I think what was most interesting was it was discovered that it's actually naturally occurring, which was a pretty big deal. Buckyballs got a lot of press in the mid-'80s and how they were going to change. So far, people still do lots of research with them, but they haven't exactly made it big time into, say, products and things like that we might use. Another element that has quite a number of allotropes is sulfur. The most common is S8. These are these chunks of yellow sulfur that you'll find lying around if you go to Yellowstone and stuff. On this picture here, I have 3 different allotropes of sulfur. I'm actually not quite sure which ones they are. However, there is even an allotrope of sulfur S2 that is a gas at room temperature. So two sulfurs, when they're together, can actually make a gas at room temperature. Now, the last allotrope, I'll just give you one last example, is phosphorus. It has a number of allotropes as well. Here are two of the more common forms, white and red phosphorus. There's actually many more kinds. For instance, there's black phosphorus, there's green phosphorus. There's a number of different kinds of allotropes of phosphorus. I'll point out that this is the structure of white phosphorus right here. It's these 4 phosphorus atoms in a pyramid shape. And unfortunately, white phosphorus is one of the worst chemicals of warfare. It's the primary ingredient in napalm, so it has kind of a bit of a bad rap because it produces very bad burns in the air when it touches your skin. So that's really all I wanted to say about allotropes. Again, let's just go back again. So again, we get that definition down. Chemical elements that exist in 2 or more structural forms. Okay, that's basically it for this short little lecture about allotropes. Have a nice day.